Hello, my name is Joe Clanin from Iowa State University, and today I'm presenting the work An Efficient Computational Strategy for Cyber-Physical Contingency Analysis in Smart Grids. The motivation for our work is the increasing penetration of cyber systems into smart grids. This has led to power systems being exposed to not only new sorts of attacks, but attacks of much larger scales. In particular, systems built to the so-called N-1 reliability criterion, wherein the failure of a single component does not critically affect the functioning of the grid, are insufficiently protected against these larger-scale attacks. It becomes necessary for system operators to perform N-K contingency analysis on their systems. This is analysis in which we consider the failure of multiple components. However, exact and exhaustive N-K contingency analysis using naive methods requires exponential time and is computationally infeasible. This raises the question of how a system operator should allocate their limited resources to mitigate the impact of attacks. In this work, we shall consider transmission line attacks in the context of a resource-constrained system operator. We model the power grid as a graph, in which the nodes represent buses and the edges represent the transmission lines. For our analysis, we adopt the linearized DC power flow model of the grid, and as our impact of the simultaneous failure of K lines, we use the notion of disturbance value, first introduced in 2017. Crucially for our work, the disturbance value exhibits an approximately modular behavior, in the sense that the disturbance value of a simultaneous failure of K lines is well approximated by the sum of the one-line disturbance values of each line in the failure set. With the disturbance value in hand, we define the following game-theoretic model of this scenario. We model this as a zero-sum game between an attacker and a defender over a set of targets given by the edges in the graph, and each of the attacker and the defender have a prescribed limited number of resources. The attacker will attack Ka lines, and the defender will defend Kd lines. This leads to a set of pure strategies for the attacker and a set of pure strategies for the defender. Now, for a given pair of strategies, one for the attacker and one for the defender, the cost to the defender is given by the sum of the one-line disturbance values for each target that is attacked but not defended. The solution concept in our additive security game model that we shall consider is that of Nash equilibrium. This will let us compute optimal strategies for the attacker and the defender. Using our game-theoretic model, we have proposed a linear time algorithm to compute an optimal defender strategy. Our result is given in terms of an optimal exposure probability vector that gives the probability that each target will be exposed when the defender plays optimally. From this optimal exposure probability vector, our approach extracts an implementation for the defender, which we obtain iteratively by choosing lines according to the probabilities in the exposure probability vector. To verify the efficacy of our approach, we have conducted simulations on the IEEE 5, 9, 14, and 39 bus test cases, which we have augmented with transmission lines to ensure that the grid remains connected after the failure of K lines. We've considered two variations on our model of the attacker in our simulations. First, we've considered a computationally superior attacker. This is an attacker that uses the exact disturbance value rather than the additive approximation. And we've also considered attackers with side information, that is, ones that have knowledge of the defender's resource constraint. And we have shown that the defender implementation we have proposed based on the optimal exposure probability vector is an optimal strategy in each of these cases, regardless of the capability of the attacker. We've also shown that the mean error of the defender outcome when compared to the exact solution is on the order of 10 to the negative 12. In conclusion, we've leveraged this near modularity of the impact metric to compute optimal security measure deployments under a resource constraint for the defender. This has led to an efficient algorithm for cyber-physical contingency analysis of transmission line failures that reduces the complexity of this procedure from exponential time to only linear time. We believe that our approach is a first step towards alleviating the exponential curse of complexity in higher-order contingency analysis. As directions for future work, we propose extending our approach to account for cascading failures, islanding, and variable line capacities, as well as applications to node attacks and dynamic attack scenarios.